In this lecture, we will be discussing about the classification of induced EMF. In the previous lecture, we have studied the phenomena of electromagnetic induction. And according to Faraday's law of electromagnetic induction, whenever the magnetic flux linking with a conductor changes, an EMF is induced in the conductor. So for an EMF to be induced in a conductor, the flux linking with the conductor should change, and this change in magnetic flux can be achieved in two ways, either by moving the conductor or by varying the magnetic field. The flux linking with a conductor should change in order for an EMF to be induced in that conductor. So in order to obtain that change in flux, we can either move the conductor by keeping the magnetic field stationary, or we can move or vary the magnetic field by keeping the conductor stationary. And depending on the method which is used for producing the EMF can be classified into two types. The induced EMF can be classified into two types, and they are named based on the status of the conductor, whether the conductor is stationary or moving. So depending on whether the conductor is stationary or moving, induced EMF is classified into two types. First one is dynamically induced EMF, and second one is statically induced EMF. And keep in mind that these names are given according to the status of the conductor. So dynamically induced EMF, dynamics, the term is related to motion. So dynamically induced EMF is the EMF produced when the conductor is moving and the magnetic field is stationary. So next one is statically induced EMF. Statically, the name indicates that the conductor is stationary. So statically induced EMF is the EMF produced when the conductor is stationary and magnetic field is varying or moving. So likewise, there are two types of induced EMF, dynamically induced EMF and statically induced EMF. In this lecture, we will be discussing in detail about the dynamically induced EMF. So for that, consider a uniform magnetic field having a flux density B Weber per meter square. So see, we have the magnetic field between a pair of poles. There is a north pole and a south pole, and flux lines are passing from the north pole to the south pole. Suppose a conductor of length L, this is the conductor, a conductor of length L is placed in the magnetic field. So this is the three-dimensional diagram. The top view of this particular diagram is shown here. The poles are not shown, only the flux lines and the conductor is shown here. So the flux lines are passing like this from north pole to the south pole. And the conductor is placed like this. On view on the top, see the conductor as a dot, which is shown here by this red. This red dot represents our conductor. Now, let initially the conductor be moved in the direction of magnetic field. So initially the conductor is placed in this particular point, and suppose we are moving the conductor in the direction of magnetic field, which is shown by its arrow mark with a velocity v. So conductor is moved in the direction of magnetic field with a velocity v. So when it is moved so, the conductor will not cut any flux lines. It will just move in a direction parallel to the line. So the conductor will not cut any flux lines, and hence EMF induced in the conductor will be 0. So when the conductor is moving like this, it is not cutting any lines, and as this is a uniform magnetic field, the flux is constant everywhere in this field. So when a conductor is moving in a direction parallel to the lines without cutting any flux lines, the flux linking with the conductor will remain constant. Okay. ഇതൊരു യൂണിഫോം മാഗ്നറ്റിക് ഫീൽഡ് ആയതുകൊണ്ട് ഈ ഫീൽഡിൽ എവിടെയും ഫ്ലക്സ് കോൺസ്റ്റൻ്റ് ആണ്. ഓക്കെ, ഫ്ലക്സ് ഡെൻസിറ്റി കോൺസ്റ്റൻ്റ് ആണ്. ഓക്കെ, സോ ഒരു ഫ്ലക്സ് ലൈനിനെയും കട്ട് ചെയ്യാൻ ലൈൻസിന് പാരലായിട്ട് മാത്രം ഒരു കണ്ടക്ടർ മൂവ് ചെയ്യും. അതിനകത്ത് റേറ്റ് ചേഞ്ച് ഇൻ ഫ്ലക്സ് ഒന്നും എക്സ്പീരിയൻസ് ചെയ്യുന്നില്ല ആ കണ്ടക്ടർ. സോ ആസ് എ റിസൾട്ട് ഇൻഡ്യൂസ്ഡ് EMF in the conductor will be 0 in this particular case. Now, assume that the conductor is moved in a direction perpendicular to the direction of magnetic field with a velocity v. Okay, so conductor is moved in a direction perpendicular to the direction of magnetic field. So which is as shown this three-dimensional diagram. See here, this particular movement is in a direction perpendicular to the direction of magnetic field. So which is shown here also. Okay. So the conductor is moved with a velocity v, and assume that after a time dt the conductor travels through a distance dx. So the conductor covers a distance dx during time dt when it is moved in a direction perpendicular to the direction of magnetic field with a velocity v. Okay. So in this condition, the conductor cuts flux lines while it is moving. So conductor cuts flux lines, the flux linking with the conductor changes, and an EMF will be induced in the conductor. Okay, this is the dynamically induced EMF, because here EMF is induced in the conductor due to the movement of the conductor. So this is the dynamically induced EMF, and we need to formulate an expression for the dynamically induced EMF. Okay. According to Faraday's law, we know that induced EMF is equal to magnitude of induced EMF is equal to rate of change of flux linkage. The rate of change of flux linkage. Okay. Flux linkage is number of turns into flux. So here we are considering a single conductor, not a coil. So we can assume the number of turns as 1. So n into phi divided by time. So n, we are assuming number of turns as 1 here. So rate of change of flux linkage will be change in flux linkage divided by time. Okay, so we need the flux, value of flux and the corresponding time. Okay. So conductor moves through a distance dx in time dt. So we need the flux linking with the conductor during this time dt. So when we divide the flux by time, we will get the value of induced EMF, because induced EMF is the rate of change of flux linkage, that is flux linkage divided by time. Okay, so we need the value of flux linking with the conductor during the time when it travels through a distance dx. Okay, but we have with us only the value of the flux density, and we have taken it as B. So we know that flux is equal to flux density into area. Flux density is flux divided by area. Okay, we have flux density B is equal to flux divided by area. B is equal to phi divided by area. So flux will be equal to flux density into area. So we have the flux density as B Weber per meter square, and if we multiply it by the area covered by the conductor while it is moving like this, we will get the value of flux linking with the conductor. Okay, so conductor is moving in this direction with a velocity v, and during that motion, during that course of movement, the conductor is covering a distance of dx in time dt. Okay, see, so the conductor is moving like this. The conductor is having a length L and it is moving like this. So here from this figure we can see that while the conductor is moving, the area covered by the conductor is a rectangle. So it covers a rectangular area. Okay, while it is moving, and that area will be equal to the length of the conductor into distance travelled by the conductor. Length into distance travelled by the conductor. Okay. So here length of the conductor is L and distance covered by the conductor is dx. So area swept by the conductor while it is moving is L into dx, because it is a rectangular area and it is equal to L into dx. Okay. So flux cut by the conductor is equal to flux density into area, that is B into L into dx. Now induced EMF is equal to rate of change of flux linkage, that is flux linkage divided by time. BL dx divided by corresponding time is dt. Okay. Now we know what is dx by dt. Dx is the displacement and dt is the corresponding time interval. Displacement divided by time gives the velocity. So EMF induced will be equal to B into L into V. Flux density into length of the conductor into velocity with which the conductor is moved. Okay. This is the value of EMF induced in this conductor while it is moving in a direction perpendicular to the direction of magnetic field. Okay. Now suppose the conductor is moving like this, okay, with a velocity v. What will be the equation for induced EMF in this particular case? So conductor is moving in a direction which makes an angle theta with the direction of magnetic field. Conductor moves at an angle theta with the direction of magnetic field. In this case, we have to resolve the velocity component into 2. So this will be the cos theta component. This will be the cos theta component. This is sin theta component. This is V sin theta. And adjacent component is V cos theta. The component adjacent to angle theta is the cos theta component. So this is V cos theta and this component, the opposite component is V sin theta. And we know that no EMF is induced in this particular direction. When the conductor is moving in the direction of magnetic field, no EMF will be induced in it. So we can neglect this particular component, the cos theta component, and we have to consider only this component, the sin theta component. So when the conductor is moving in a direction which makes an angle theta with the direction of magnetic field, the induced EMF will be proportional to the component of velocity which is perpendicular to the magnetic field. So in this particular case, the induced EMF will be proportional to the component of velocity which is perpendicular to the magnetic field, that is the V sin theta component. So here instead of V, we have to use the V sin theta component. So equation for induced EMF is BLV sin theta. This is the general equation for dynamically induced EMF. BLV sin theta, flux density into length of the conductor into velocity of the conductor into sine of the angle which the conductor makes with the direction of magnetic field. So this is the general equation. By substituting the value of theta in this particular equation, we will get the induced EMF when the conductor moves in any direction. Okay. So initially we have seen that when the conductor is moving in the direction of magnetic field, induced EMF is 0. That is theta is 0 in that case. So if we substitute theta is equal to 0, it will be sine 0. So EMF is 0. Now in the second case, we have assumed that the conductor is moving in the direction perpendicular to the magnetic field. So in this case, angle theta is 90 degree and sine 90 becomes 1. So induced EMF is BLV. That is the value that we have obtained in the previous case, which is the maximum value of induced EMF. So induced EMF becomes maximum when sin theta is having its maximum value, that is 1. So induced EMF, maximum value of induced EMF is BLV, flux density into length of the conductor into velocity, okay, and which is obtained when the conductor is moving in a direction perpendicular to the magnetic field, and this is the general equation for the conductor, for the conductor induced EMF. The next is Fleming's right hand rule, and it is used for determining the direction of dynamically induced EMF or the corresponding current. Okay, Fleming's right hand rule is used for determining the direction of dynamically induced EMF or the corresponding current. So according to Fleming's right hand rule, in order to find the direction of EMF, stretch out the thumb, forefinger and middle finger of the right hand in mutually perpendicular directions as shown in this particular figure. Stretch out the thumb, forefinger and middle finger of the right hand in mutually perpendicular directions in such a way that the thumb pointing in the direction of force or direction of movement of the conductor. Then the forefinger in the direction of magnetic field. Forefinger in the direction of magnetic field. Then the direction which is given by the middle finger will be the direction of current or induced EMF. So here in this diagram, suppose we are moving this conductor up and down, okay, or we are going to, in a particular case we are going to move the conductor upwards. That is why we are placing the thumb like this, okay, thumb pointing in the upward direction. Then magnetic flux lines always pass from north pole to south poles, so the forefinger is stretched in this direction towards the south, okay, and when these two fingers are stretched out like this, the third finger, the thumb, will be in this particular direction. That means current will flow like this. Current will flow in this particular direction. That is Fleming's right hand rule.